Hello and welcome. We are going to solve a turbine problem involving a gas, air in this case, flowing through a steady state turbine, and we are supposed to find the maximum power this turbine can deliver, as well as finding the isentropic efficiency and the exergetic efficiency, the second law efficiency. I've already marked the inlet and exit states. 1 is my inlet state, 2 and 3 are the isentropic exit state, and as you can see, entropy remains constant between 1 and 2, and 3 is the actual exit state of this turbine. In that case, the turbine efficiency or the isentropic efficiency is the power that is delivered by the actual turbine between 1 and 3 and the isentropic turbine 1 and 2. Note that 2 is a theoretical exit state, an isentropic exit state that may not be a real exit state, hypothetical exit state. On the other hand, to find the exergetic efficiency, it is the useful work between 1 and 3, the actual turbine, and the reversible turbine that will operate between the same state 1 and 3, not a fictitious state like the isentropic state. In other words, between 1 and 3, if we remove all the sources of irreversibility, there is no entropy generation, what will be the output? And that's called the reversible work output. So this is our second law or exergetic efficiency, and this is our isentropic or turbine efficiency. Okay, so let's go and set up these states and evaluate this work. I've already logged in as a student, and you going to the TESTapps page, we realize that for a turbine, we'll follow the open system, a generic branch, and single flow device. And this is a gas turbine. And the problem, I believe it says use the PG model. So we launch the PG model. Okay, it's time to evaluate the states. Air is already the chosen fluid. So what we need to do is to evaluate the inlet and exit states first. 4 MPa is my inlet pressure, 600 degrees Celsius is the temperature of the inlet state, and the mass flow rate is given as, oops, there is no volume flow rate, 5 kg per second. We are, of course, neglecting the Ke and Pe, so they are set already by default at 0. For state 2, the exit pressure is 200 kPa. It's isentropic exit state. So entropy must be equal to state 1, and of course, mass flow rate doesn't change. And we can go to the device panel, set up the perfect or ideal device, isentropic device. State 1 and 2 are my inlet and exit states. Of course, there is no heat transfer, and so the maximum possible work output is W.external 2521 kilowatt or 2.52 megawatt. So this is the ideal turbine output. Okay, so let's go and find the actual exit state. So instead of creating a new state, we'll just spawn it using this button. It's a very convenient button. What happens is that we just duplicated state 2 as state 3, and we'll just modify it instead of, so everything else is same except the exit temperature is 220 degrees Celsius. So state 3 is calculated. If you go to the graphics panel, state 3 is the right of state 2. That means the actual exit state has a lot of entropy generation involved. Okay, so device 2 is my actual turbine between state 1 and state 3. Again, it's adiabatic, so therefore the actual work is calculated now. So W.external 2 is my actual work. So what is the isentropic efficiency? Let's go to the user code and let's define a variable called eta turbine is W.ext2 is my actual, W.ext1 is the ideal or the isentropic turbine. So their ratio should be the efficiency. and that's 75.63%. Okay, now that we know the turbine efficiency, let's go and see how we evaluate the exergetic efficiency. For that, we turn on the include exergy button. Exergies are now included. Notice that phi and psi are now included. Without this variable will not appear. So to calculate the exergy, we need to first declare the dead state, and the dead state pressure is given as 100 kPa, temperature is given as 298 Kelvin. So once the dead state is calculated, of course it has a stored exergy of 0. It's a dead state by definition, exergy should be 0. Then therefore state 1 automatically exergy is updated. Notice there's a huge amount of exergy. Exergy meaning how much useful work you can extract at the most from a given state. That's the definition of exergy really. State 2 and 3, they're all updated for exergy. So you go to the device panel now, and for this real device, we basically, everything is set there. The exergy Q dot 2 is 0, and by definition, by default, Q dot atmosphere is set to 0. Therefore, everything is automatically calculated. Essentially, the heat transfer can be distributed between, in the device panel, between two sources. One is Q dot B and one is Q dot atmosphere. And the Q dot atmosphere is the one we can assign, and Q dot B is automatically calculated. In this turbine, there is nothing, there is no other heat transfer other than atmosphere. Actually, even that is 0. So once this is set to 0, everything else is calculated. So therefore, we now know what is W dot reversible. And of course, the W dot useful is the external work. This will be the same as the useful work, as you can see. So their ratio will be the isentropic or the second law efficiency. So therefore, in the IO panel, we can declare eta exergetic efficiency, eta exergy as a new variable. Again, W dot ext2, or we could say W dot useful 2, W dot reversible 2, and that should give us the exergetic efficiency. As you can see in the output panel, it's calculated as 81.7%. So basically we are done. We have found the efficiency, the turbine efficiency or the isentropic efficiency and the exergetic efficiency. The exergetic efficiency means that that's 81% of the energy that could be exploited has been exploited. The rest could not be because some has been destroyed by entropy generation. This is the rate of exergy destruction, and the whole reason for that is friction inside the turbine. So if that is eliminated, we'll have 100% exergetic efficiency without changing the exit conditions.